Assalamu alaikum and welcome back to our channel. Today we begin a focused technical review of the evolution of convolutional neural networks. This is the history of how computer vision developed, showing the progression of core architectures from early LeNet to the latest transformer-based models. Each step in this sequence solved a major technical problem and advanced our capability of visual intelligence. We will focus only on the image classification models in this video. Before CNNs, we used traditional artificial intelligence networks. They struggled with images for two big reasons. First, computation. A single 224 by 24 image means more than 150,000 inputs. This created millions of parameters and made training painfully slow. Second, the spatial understanding. ANN saw each pixel as an independent and isolated value. They didn't know that neighboring pixels form shapes or edges. If you move an object slightly, the network failed to recognize it. CNN changed that mechanism. They introduced convolutional layers that learned local patterns, pooling layers that reduce the dimensions, and deeper hierarchies that build up from edges to texture to fill objects. The story begins in 1998 with LeNet 5, created by Jan LeCun and his team. This architecture is a true pioneer and laid the groundwork for modern scenes. It was designed to read handwritten digits on checks and postal codes. It was small, but it was the very first network that learned directly from the raw pixel data. LeNet used convolutional layers to capture patterns, pooling layers to compress information, and fully connected layers at the end to classify the digits. It proved that neural networks could understand the visual structure. But the progress stalled. We didn't yet have enough data or computing power to train bigger models. That changed in 2012 when AlexNet appeared and transformed the computer vision overnight. AlexNet was deeper, wider, and trained on GPUs. It crushed the ImageNet computation by a massive margin and showed the true potential of deep CNNs. It replaced slow sigmoid activation with ReLU, which speed up training and fixed the vanishing gradient problem. It used dropout to reduce overfitting and data augmentation to make the model robust to variations. This was the model that sparked the deep learning revolution. 2 years later, in 2014, came ViT from the Visual Geometry Group at Oxford. It didn't rely on new tricks, but proved the power of depth and simplicity. ViT used small 3x3 filters stacked repeatedly, showing that deeper networks could achieve larger deceptive fields efficiently. Its clean, uniform structure made it easy to scale and set the foundation for many later architectures. But ViT had a problem. It was computationally heavy. That same year, Google tackled this problem with GoogleNet, known as Inception V1. Instead of going deeper, GoogleNet went wider. It introduced the Inception module, which ran several convolutions of different sizes in parallel and merged their output. It also used one-by-one convolution to reduce the number of channels before larger filters, cutting the computational cost drastically. It replaced dense fully connected layers with global average pooling, reducing the overfitting. GoogleNet achieved better accuracy with fewer parameters and changed how we thought about efficiency in CNN. By 2015, networks were getting deeper, but a new problem appeared. Adding more layers started to hurt the performance instead of improving. Training became unstable and accuracy degraded. Microsoft Research solved this problem with ResNet. ResNet introduced residual connections, short paths that let the information skip the layers. These shortcuts allowed the gradients to flow smoothly during the training and made it possible to train networks with over 100 layers. ResNet fixed the degradation problem, set new records, and made the foundation for most modern vision models. In 2017, DenseNet took the idea of connectivity even further. Instead of connecting only to the next layer, every layer connected to every further layer. This design encouraged feature reuse, improved information flow, and surprisingly very fewer parameters than ResNet. DenseNet showed that the smarter connectivity could outperform brute force depth. As deep learning moved towards mobile and embedded systems, efficiency became essential. That's where MobileNet came in. It used depth-wise separable convolution, breaking a standard convolution into two simpler operations. This reduced the computation drastically while keeping the strong accuracy. MobileNet made CNNs practical for mobile phones, drones, and edge devices. Then in 2019, Google introduced EfficientNet. Instead of scaling width, depth, or resolution separately, it introduced compound scaling, which balanced all the three. This made models far more efficient. Efficient achieved top accuracy with the fewer parameters and became a go-to backbone for many vision tasks. This proved that better design could outperform raw size. But the next leap didn't use convolutions at all. Vision transformers, or ViTs, borrowed the self-attention mechanism from natural language processing into the vision. They split the images into small patches and treated them as sequence. Each patch attended to every other, capturing a global context across the entire image. With enough data and computation, ViT surpassed the CNNs or large-scale benchmark datasets. They showed that attention could replace the convolution altogether. Still, CNN didn't disappear. They evolved again. Models like Next took ideas from the transformers and modernized CNNs with larger kernels, layer normalization, and improved training design. Meanwhile, hybrid architecture combined the convolution for local details and attention for global structure, blending the best for both models. From LeNet, recognizing digit in 1990s, to today's transformers powering multi-model AI. This evolution has been one continuous path of solving one limitation after another. Each model learned from the previous one and move us closer to machines that truly see. Which of these architectures do you think made the biggest impact? Share your thoughts in the comments and stay tuned for the next video where we will explore how these architectures evolved for object detection.